Yep.
All right. So first off, I'd like to thank Concordia University for their support. This summer's research was done with the aid of a Concordia Undergraduate Student Research Award. And the title of my presentation is Number Theory Meets Machine Learning. It's a timeline of this summer's research. I worked on jointly with Simone Brugiapaglia and Giovanni Rosso. I would present a highly interdisciplinary research project at the intersection of pure and applied math and motivated by the recent breakthroughs in machine learning, specifically deep learning. And we decided to see if these tools could be used to tackle a tough number theory problem. The notorious Collatz conjecture. So the Collatz function is a piecewise function on the integers, where if the input is odd, then 1 multiplies by 3 and adds 1. And if the input is even, 1 divides by 2. So the Collatz function is used to define the sequence of hailstone numbers recursively for any positive integer as initial value. So to get an idea about hailstone numbers, I'll go over a simple example. So consider h naught equals 17. You start off with 17, which is odd. So then you multiply by 3, you add 1, you get 52, which is even. So you divide by 2 to get 26, which is even again. And you divide, and you end up getting to 13. So eventually you end up getting a 5, which is odd. So you multiply by 3, add 1, and you get 16, which is 2 to the 4. So you end up dividing by 2 4 times, and you reach 1. And then once you reach 1, you end up getting a cycle. So 1 cycles with itself, as you can see at the bottom here. So 1 gets mapped to 4, which eventually gets mapped to 1 again. So the question everyone is dying to know the answer to is, does every positive integer eventually reach 1, starting as an initial value in the sequence? So this has been verified as true for all positive integers less than or equal to 2 to the 68, and the record is held by David Barina. That's not how you pronounce his name. It's a Czech pronunciation. I really can't pronounce it, so I'm really sorry about that. So if you were wondering if the negative integers could also be included with reaching -1 instead of 1, take, for example, h naught equals -5 or -17. You can see here that -5 is cyclical with itself. So the usual example to demonstrate the complexity of such sequences is initial value 27. So it's a number less than 100 that takes a comically long time to get to 1 compared to all the positive integers less than 27. And the first sequence you see here has 111 steps. So is every number in the sequence important, or are some numbers stated uselessly, acting like noise in the background? There are subsequences which skip over intermediates and provide an acceleration, thus reducing the noise. So a common acceleration in the literature is to use the t function, because 3x plus 1 can be divided by 2 straight away if x is odd. So you can see here, instead of 3x plus 1, it's 3x plus 1 divided by 2. So this reduces the steps to 70 for this sequence here. And another common acceleration in the literature is to only consider the odd numbers in the sequence, hence the Syracuse iterates. So the Syracuse iterates are an acceleration on the even numbers of the sequence. So they factor out all powers of 2 immediately once an even number is reached. And so I was wondering if there was a similar acceleration that could be done for the odd numbers. So it's known that 2 to the pi times theta minus 1 maps to 3 to the pi times theta minus 1 for pi and theta natural numbers and theta odd. It's an easy result using induction and the t function. And I figured this out on my own, but I'm not the first one to figure it out. I think this result is known since 2006. So using this acceleration and the Syracuse acceleration on the even numbers, for example, one erases many intermediate steps starting from 863 to 205. So I would say 863 maps to 205 in one superstep. So I originally called this combination of accelerations the Montreal iterates, given that they are a slight add-on to the Syracuse iterates, and given how close Montreal and Syracuse are on the map. And 27 needs only 17 of these supersteps to get to 1. So that defines them. That defines the Montreal iterates mathematically. This formula here. But I think they're best described pictorially. So they're described as connecting. Here you can see as connecting consecutive minima on the graphs of hailstone numbers defined using T. And intuitively, they could be said to cut the spikes of the graph. So now I can define the helper function. So the helper function is a stopping time function and is defined in terms of the Montreal iterates. It takes as input a positive integer and returns the minimum number of supersteps to get to 1 with initial value x. I arbitrarily defined it to be 0 at 1 because no supersteps are needed to get to 1. 1 is already there. So the inspiration for this summer's research came from what looked like a pattern in the upper bounds of helper for odd initial values in some interval with length of power of 2. So for all odd initial values less than 2 to the 10 here, so 2 to the 10 is 1024. So for all odd initial values less than 2 to the 10, 871 requires the maximum of 27 or 3 to the 3 steps, supersteps, sorry. While for all odd initial values less than 2 to the 20, 83,007,799 requires the maximum of 81 or 3 to the 4 supersteps. So 3 cubed, 3 to the 4, 2 to the 10, 2 to the 20. Is this a coincidence? So far so good up to 2 to the 30. It looks like helper is bounded above by numbers made up of powers of 2s and 3s. So helper on the interval 1 to 2 to the 5 is bounded above by 18, so 2 times 3 squared. And on the interval 1 to 2 to the 30 is bounded above by 157, which is really close to 162, which is 2 times 81, or 2 times 2 to the 4. So now Eric Rosendahl has a website called 3x+1 where he has a host of records, and he has something called the delay records, and it's the total number of steps required before getting to 1. So they don't necessarily correspond exactly to the delay records in terms of helper, but they correspond well enough. So in a 2 to the 60, we can see that's when the pattern starts to break down using the delay records from Eric Rosendahl's website. So if you run a computer check, the 2 closest numbers to 339 that are products of 2s and 3s are 324, which falls short, and 384, which goes way over the bound. So this is an example of like thinking you're on the right track and then hitting a wall, which is not so infrequent when working on collabs, and why the conjecture is so hard to solve. So I think Kevin Hartnett said it best in his article, Mathematician Proves Huge Result on Dangerous Problem. It's an article on Terence Tao's work on the conjecture and his warning not to work on it. So he says, just when you think you've cornered the problem, it slips away. And I think this problem eats up and spits out attempts at solving it, much like it eats zeros and ones of numbers written in binary notation, returning a 1. So here's a little monster eating 1s and 0s. So regardless, there have been some recent breakthroughs, as I've mentioned. There's been a monumental breakthrough on Terence Tao's part. He recently uploaded a paper to the archive in June of 2020. called almost all orbits of the Pullats map attain almost bounded values. And more recently, in the computational direction, Yoku, Aronson, and Euler uploaded a paper to the archive, an automated approach to the Pullats conjecture, explorations with rewriting systems, matrix interpretations, and SAT in May of 2021. And I think that paper was 4 years in the making. So now for the machine learning part. So like I said, the summer's research was to try some new ideas on Pullats with the humble goal of watching them fail, probably. But deep learning being extremely popular with mainstream media coverage of the successful computer program AlphaGo, self-driving cars, digital image processing, and deep learning has found applications basically almost everywhere. So with applications such as black and white photo slash color video coloration. So you can see this video was in black and white and now it's in color. Translation, music composition, art generators, and even predicting earthquakes. So with this powerful tool proved useful in number theory. And I think after all, Pullats being verified up to 2 to the 68 has no shortage of data. So I think Victor Jou's blog post, Machine Learning for Beginners, is a nice introduction that requires no more than multivariable calculus and linear algebra. So here's a short summary. A feed-forward neural network is a collection of neurons connected in layers, and the inputs are fed forward layer by layer. So here's the input layer, here's the hidden layer, and here's the output layer. So neurons are a function that takes in a vector as input, and the vector is dotted with a weight vector here, W, and a bias is added to the product, and this number is now passed through a activation function, F. There's multiple activation functions. I think sigmoid and ReLU are popular, are good examples. And sigmoid is called as such because it looks like the letter S. So now we would like to have the right weights and biases, such that given a specific input, we get the desired output. So a loss function needs to be defined. There's also various loss functions as well. However, I think MSE or the mean squared error is a good example. So one would like to compare what the output is and what it should be. So that is like y predicted and y desired. And the mean squared error is the average of the squares of these differences. Since the output of a neural net depends on the weights and biases, we can think of the loss function as being a function of the weights and biases, as you can see here. Another goal of training the network would be to adjust the weights and biases so as to reduce the loss as much as possible. So there's also various algorithms to adjust the weights and biases to reduce the loss function. One of them being stochastic gradient descent. So the weights are subtracted by some positive constant eta, the learning rate, times the partial derivative of the loss function at the weight w sub I, and the biases are adjusted through a similar process. And we say stochastic, so the process I described is gradient descent, but it becomes stochastic gradient descent if you do this for some sample of the data set, because you can find that maybe it's too computationally costly to do for the entire data set. And now this brings me to the notion of epoch. So an epoch is basically, if you're using stochastic gradient descent, it's once the model has trained on the entire data set. So you would take subsets, and you can choose the subsets at random, or you could choose the subsets systematically. But once the model has trained on every single point in the data set, that would define an epoch. And so this process can be iterated for as long as you want your experiments to run, or however many epochs you choose for your experiment to run for. And this will hopefully reduce the loss over time. So here's an example of a loss function reducing to almost zero after 1,000 epochs. So a little history behind artificial neural networks. Artificial neural networks are an old idea. They were inspired by biological neural networks inside animal brains. And in 1958, Frank Rosenblatt created the perceptron, a machine originally designed for image recognition. Now, perceptrons showed promise at the time, but it turns out that feed-forward neural networks, or a multi-layer perceptron with 2 or more layers, proved to have greater processing power. So I know I said deep learning at the beginning, but the deep learning comes from the depth of the network. That is, an artificial neural network with many hidden layers. So you can see here there's many hidden layers. Well, there's 4 hidden layers compared to 1. So deep learning with artificial neural networks use data to create a model to make predictions, unlike programming a computer to create the data. Here, the data creates the program. So these concepts existed. They're rather old, but the programs were not practical to run because of a lack of computing power. So a lot of the rapid innovation we see today in deep learning that started around 2010 was backed by advances in GPUs. So these things, or graphics processing units, basically the things that make your realistic online games not lag. So in some sense, video games subsidize advances in GPUs, which then proved extremely useful in allowing artificial neural networks to handle large data sets. So in the end, we settled on trying to see if a machine learning problem could be formulated about collax using the simplest deep learning model, a feed-forward neural network. So we gave it. We started to brainstorm like what would be a good problem to tackle related to collax that we could use machine learning for, and a model that would tell you if the next number arrived at 1 after being trained on a set of numbers that do go to 1. We decided it would be too biased because every number in the training data does converge to 1, so the model would predict that all numbers converge to 1. So we decided to see if we could try and explain some of the weird behavior of the helper function. So why does helper jump from, you can see here, why does helper jump from 5 to 17 at 27? So for all values less than 27, helper requires at most 5 supersteps, but then at 27, you see this large jump to 17. So I originally thought the patterns in the upper bounds of helper might be the explanation. So I thought helper needed an upper bound of about 18 on the interval 1 to 32, but we saw that that line of reasoning quickly broke down. So the idea was to create a hole at 27 in the data, train the model on the rest of the data, and see how well the model predicted the value at 27. So we made a data set of all odd positive integers less than 2 to the 10, and there's corresponding helper values. So you can see here there's 511 rows. With 27, 17 popped out. And then we built a feed-forward neural network using Keras and Google Colab. So I ran multiple experiments to create a dashboard to see what were the best set of parameters, and it turned out that a depth of 8 layers and 512 neurons per layer. So you can see these are the layers here, and there's 512 neurons per layer. With Adam, a variation of stochastic gradient descent and a learning rate of 10 to the -4 perform the best in terms of reducing the loss. So I played around with activation functions as well. Sigmoid didn't perform as well as ReLU, so we ended up sticking with ReLU for the rest of the experiments. And after 10,000 epochs, with a validation split of 0.2, regardless of the parameters tested, the model is not able to reduce the loss below 25. And this is the best model. So even if it gets close to 25, the validation loss here increases chaotically. So this suggests more of a memorization of data, and that's not what we want. So turns out that this problem is too difficult for this particular choice of model, suggesting that there's too much noise in the data. And well, this shouldn't come as a surprise because this is how most things go with COLATs, really. So far, COLATs 1, machine learning 0. So this is a picture of the predictions versus the data. So the white is the model and the dots are the data. So that's the feed-forward network's attempt to try and predict what the values of helper are. So we thought, what about a average version of helper? So I define here helper adjusted. So it's essentially helper, but equal to 0 for negative inputs, and for inputs of 0 as well. And I define helper average. So helper average takes in 2 inputs. So it takes in input x, which is here, the center of the sum, and input k, which defines how many points are taken symmetrically to the left and right of helper. And then all these are added together and then divided by 2k plus 1, which is how many numbers we have in the sum. So here's a little animation of k increasing from 0 to 10. So this is 0, 1, 2, 3, 7, 8, 9, and 10. So the model performs well, predicting accurately the value of helper average as low as k equals 3 and better as k increases to 10. So I did not test for k larger than 10 because helper adjusted is defined to be 0 for negative inputs. So it's going to suck in the values the more numbers you take to the left and right. So here's k equals 1. And you'll see the validation loss and loss converge as k increases to 10. And so here's the predictions. So k equals 0, obviously a bad prediction. It predicts 6.1, whereas helper is really 17. That's no surprise. So here, 1 and 2, we can sort of, 2 is not that bad, 8.8 to 8.5. I think 3 does really well. So 3 predicts 7.3 versus 7.28. And then 8 is probably the best. So predicts 5.846. Upper average is 5.882. And you can see the rest don't deviate too far from the actual value of helper average. So we'd like to conclude with some open problems. So obviously, we'd have liked to apply more advanced deep learning techniques to the COLATS data set, in particular time series forecasting. Time series forecasting is used to predict stock market prices, and graphs of hailstone numbers resemble graphs of stock market prices with similar volatility. We wanted to test how far helper is from a pseudo-random sequence using the diehard test created by George Marsalia. And there's also some signal processing ideas that we wanted to try on graphs of hailstone numbers. Thank you for your time.
Thanks so much, Brendon. Everyone give a round of applause either through emoji form or actual applause. Thank you so much. We really appreciate your talk. Brendon, if you're comfortable, you can toss some contact info in the chat in case anyone has any questions, just because we are going to be transitioning to the next talk right now. And for everyone else, feel free to stay in this room if you'd like to see the next talk by Ryan Edwards introducing determinantal facet ideals. And if not, feel free to hop into any of the other rooms to see any other talks, but totally up to you. But yeah, that is everything. I'm also going to stop